Hello to my favorite class. Sorry I can't be there this week, um, but I'll be back. If you didn't get the message on Google Classroom, make sure you keep an eye on Google Classroom to get the latest information from me. But in the meantime, the plan is we're going to have video lessons on Monday, Thursday, Friday this week, and you can do your homework right in class after you watch the video. And then on Tuesday and Wednesday, I'm gonna be live on the regular Google Meet link and answer any questions you have on the Unit 6 personal progress checks. The Unit 6 test, instead of being Thursday and Friday this week, it will be sometime in the future after I return. So it'll probably be next week. I'm thinking like Tuesday or Wednesday, but it depends on when I'm able to come back. I think I'll be able to come back Monday, but I'm not exactly sure of that. So I'll have to get back to you on that. But tentatively, let's just plan on Tuesday and Wednesday of next week for the Unit 6 test. Okay? In the meantime, today we're going to talk about going to and from definite integrals and Riemann sums. Okay, we talked the other day about writing a Riemann sum as a summation using the capital sigma notation. So we came up with something like this. Like if you have the integral from a to b of f of x dx, then it's approximately equal to the sum from k equals 1 to n of like f of x sub k times delta x. Think of it that way. This is like the height of each rectangle, and this is like the width of each rectangle. N is the number of rectangles, right? So in this formula, n is the number of rectangles, right? Delta x, remember, was really like b minus a divided by n. It's the total width of the interval that you're integrating over divided by the number of rectangles that you want. And x subscript k was really like the initial point a plus b minus a over n times k, right? So think about that. This is like a plus however many widths you wanted to go over, right? So the first height would be calculated at a plus 1 width of a rectangle. The second height would be calculated at a plus 2 widths of a rectangle. That's the second rectangle over, and so on and so forth, right? So if you kind of put all that stuff together, this ends up being the integral from a to b of f of x dx equals, or approximately equal to, the summation k equals 1 to n f of a plus b minus a over n times k, right, times b minus a over n. And definitely it's true. Remember, as n gets bigger and bigger and bigger and bigger and bigger, this approximation gets better and better and better. So that's limits, right? That's limit language. We could actually say that the integral from a to b of f of x dx would actually equal the limit as n goes to infinity of that whole thing. Summation k equals 1 to n f of a plus b minus a over n times k times b minus a over n. A definite integral is really the limit of the Riemann sums as the number of rectangles you're adding together goes to infinity. So hopefully this makes sense to you. This is like a key idea, right? The definite integral is the actual area under the curve. This thing right here is an approximation for the area under the curve. And as n goes to infinity, that approximation gets better and better and better, which means that the limit as n goes to infinity of that summation is equal to that actual area. So what we're going to focus on today then is actually changing from one to another. If I know that definite integrals are equal to this, well, what if I'm given a definite integral? How do I write it like this? And what if I'm given one of these? How do I write it as a definite integral? Okay, so that's what we're going to talk about. So like, for example, suppose the definite integral that I'm starting with is the definite integral. Let's say we're going from I don't know, 2 to 5 of 3x squared. And the directions would say, write this as the limit of Riemann sums. Okay? Well, you got to figure out a few things, first of all. Like we know that, for example, delta x, the width of each of those little rectangles is really 5 minus 2 over n. Right? 5 minus 2 over n. So what we're going to do here is we're going to take we're going to take the limit as n goes to infinity. This is equal to that. The limit as n goes to infinity of the sum k equals 1 to n. Right? Now it's going to be, I'm going to write it in 2 steps. You don't necessarily have to do this, but I'm going to. This is going to be f of x sub k times 3 over n, right? Because that's the width of each interval, 3 over n, right? Now, this f of x sub k is really going to be limit as n goes to infinity, summation k equals 1 to n. It's really going to be what you get when you substitute x sub k into the function. But x sub k is really 2 plus 3 over n times k. Right? That's what x sub k is. It's that amount. So you're going to plug this into the original function. So it's going to be 3 times 2 plus, maybe they'll write it as like 3k over n or something. That's fine. Times, or squared, times 3 over n. That's it. That's all you're going to do is just rewrite it using the summation notation instead. Okay? If I had another one, let's suppose I had something like, what if it was like the integral from 5 to 12 of ln x dx. This would just be the limit as n goes to infinity of the summation k equals 1 to n of ln something. Now that something is going to be 5 plus 12 minus 5, 7 over n k times 7 over n. Done. Okay, the width of the rectangle is going to be, that's this amount, it's going to be 12 minus 5 divided by n, 7 over n. That's where that number comes from. This right here is always going to be a plus that, 7 over n, times k. Okay, the a value in this case is 5. So that's where I got this 5 plus 7 over n times k. That's it. There's really nothing more to it. If the integrand had more than one term that had an accent, like for example, suppose it was something like the integral from -2 to 3 of x squared plus 5x. This would just be the limit as n goes to infinity of the summation k equals 1 to n. Now I'm just going to, the xk thing, the x sub k, in this case is going to be -2 plus, if I subtract these, I get 5 over n k, right? That's x sub k. So I'm going to plug that into both of these x values. It's going to be -2 plus 5k over n squared plus 5 times negative 2 plus 5k over n. That's the height of the rectangle times 5 over n. That's the width of each rectangle. Okay? So that's the first part of the assignment, is going from a definite integral to the limit of Riemann sums. The second part of the assignment is just going the opposite way. Okay? So you just have to like identify all the parts. All right? So like, for example, suppose I had something that was like the limit as n goes to infinity. Let's say it was like the summation of k equals 1 to n of square root of 4 plus 5i, or 5k over n times 5 over n. Something like that. Okay. And they say write this as a definite integral. Well, the first thing that I would do is I would look at this last part and say, well, this is actually the width of the rectangle. This is b minus a over n. So we know that b minus a has to equal 5. That's the width of the interval. It's 5 units wide, right? That's the width of the whole interval that you're integrating over. The stuff that's in here is really a plus 5k over n. Well, so the a has to be 4 in this case, right? So if a is 4, but the width of the interval is 5, that means that the lower limit of integration is 4, but the upper limit has to be 9 because it has to be 5 units. And in this case, it's just radical x dx. Done. Okay, so once you've identified all those parts, that's all there is to it. So what if I had something that was like the limit as n goes to infinity of the summation k equals 1 to n. And let's say this time it's like sine of pi over 2 plus, let's say it was like 2 pi k over n times 2 pi over n. Okay, I know that this is going to be the integral from pi over 2, because this is a. And then to get the top limit of integration, I'm going to add this amount to it because that's the width of the interval. So if you go pi over 2 and you add 2 pi to that, right, that's 4 pi over 2, you get 5 pi over 2, right? That's the top limit of integration. Sine x dx, done. Okay, so tonight's homework is on AP Classroom, and it's just a handout where you got to do a few of each of these. Okay, hopefully it's not too tough, but that's the whole idea, just changing from one to another. And this is one of those topics that it's like there'll be one question, it'll be multiple choice on the AP exam, and if you know it, you know it, and that's the point. And if you don't know it, that's another thing you got to make up someplace else. So I think this stuff's kind of easy if you get the idea and the pattern. If you don't get the pattern, it's much harder. So if you're still having a problem after this, you can ask me questions, or I'd encourage you, like, watch a Khan Academy video or something like that, and it's super clear on there. I guess that's it. So once again, smash that like button and keep it fresh.